Okay, today we're talking about finding limits, and we're going to specifically be talking about finding limits numerically and graphically. And so this is a calculus topic, and calculus is the first thing that you'll study, finding limits. And when we talk about limits, a limit is an analysis of what happens to a function as the variable x approaches a particular value, a given value. The limit is the y value, okay? Critical, very important. A limit is a y value. Okay, so you're looking at a y value as the function approaches, and this is important, approaches, but is not necessarily equal to as x approaches a given value. Okay, so when you talk about a limit, it's a y value of the function that the function is getting very, very, very close to. Okay, but it's not necessarily actually getting there. And so the most common one that you're familiar with would be if you've got a horizontal asymptote, you've got a vertical asymptote, and we talked about graphing rational functions that approach this horizontal asymptote. They never really get there, but as x is going towards infinity, the y value is approaching 0. And so 0 is considered the limit of the function as x approaches positive infinity. Okay, so this is our limit notation right here. It's read the limit of f of x as x approaches a is equal to L. L stands for limit. We use a capital L to reference a limit. And we read this, the limit of f of x as x approaches a. Or you might say the limit as x approaches a of f of x. Either one is okay. And so our first examples that we're going to look at deal with using a table of values to estimate the y value that the function is approaching. So in this example, y equals x squared minus x plus 2. We're using a table of values to find the limit as x approaches 2 of x squared minus x plus 2. So in our table, the first number that we're going to plug in is 1, and when I plug it into the function, I get 2. If I plug in 1.5, I get 2.75. If I plug in 1.9, I get 3.71. 1.99 gives me 3.9701. 1.999, 3.997. Notice that my x values are getting closer and closer to 2. Then coming from the other direction, starting at 3 and working my way back to 2, when I plug in a 3, I get 8. When I plug in a 2.5, I get 5.75. 2.1 gives me 4.31. 2.01 is 4.0301. 2.001 is 4.003. So what we're looking at is as my function is approaching 2, this one is from the left, these values are from the left, these values are coming from the right of the graph. As you're approaching 2 from the left and from the right, what y value are you getting close to? Well, in this case, it's the y value right in between 3.997 and 4.003. So your function is approaching the y value of 4. So we would say that the limit is equal to 4. So part B says, what do you notice about the y values as we get closer to x equals 2? Well, they get very close to 4. So evaluating the limit as x approaches 2 of x squared minus x plus 2 would give you a value of 4 for the limit. So we're basically taking a table of values and looking at the y values as x gets very, very close. And so we want to be very, very close. Notice there's 3 decimal places here, 0.001 and 0.999. That gets you very, very close. You could get even closer by adding another digit to it. Okay, the closer you get, the better your approximation will be. Okay, so this example, y equals 1 over x. Using a table of values, find the limit as x approaches infinity of 1 over x. So in this case, x is getting infinitely large. So I want to pick x's that are getting infinitely large. So when I plug in a 1 to 1 over x, I get 1. 100, I get 0.01. 1,000, I get 0.001. 100,000, 4 zeros and a 1. 10 million, I've got 1, 2, 3, 4, 5, 6 zeros and a 1. So what do you notice about the y values? Okay, the y values as the x values get larger and larger. Well, they are getting smaller and smaller. The key to this, though, is that even though they're getting smaller and smaller, they're never going to go negative. So the smallest they could possibly get to would be just before you hit 0. So they're getting closer to 0. So based on that, when you evaluate the limit as x gets infinitely large, that would be equal to 0. Okay, now part D says, what do you think is the value as x approaches negative infinity? Well, what values would you have been plugging into your table if x was getting infinitely small? Well, you would be plugging negative values that are getting infinitely big. So -1, -10, -100, -1000. And so this your y values that your function is approaching as x is getting infinitely small are still getting very, very, very close to 0, but they're coming from the underside. They're coming from the negative side, but they're still approaching 0. And so they still approach 0, so the limit as x approaches negative infinity of 1 over x is also going to be 0. And if you think about that graphically, what happens when you graph this function, 1 over x, you have a function that looks like this, the graph that looks like that, with the horizontal asymptote and a vertical asymptote on your y-axis. And so as x goes towards positive infinity and towards negative infinity, it's approaching 0 in both situations. So let's talk for a minute about what we call one-sided limits. One-sided limit is a limit that's only coming from the left or from the right-hand side. And so the notation for a one-sided limit is with a little plus sign or a little minus sign as an exponent on the value that x is approaching. Okay, so the plus sign means coming from the right-hand side. The minus sign means coming from the left-hand side. And so we read this, the limit as x approaches a from the right of f of x, or the limit as x approaches a from the left of f of x. And so the key to this one-sided limits business is that sometimes a function will only have a right-hand limit or a left-hand limit as x approaches a specific value. For instance, with this function here, I'm not sure if you can read that, it's a little y equals x over the absolute value of x. This is what its graph looks like. And so if I'm approaching 0, 0 from the left, the y value that it's approaching is -1. Approaching 0 from the right, I'm approaching a y value of +1. So the limit from the left is not the same as the limit from the right. And so for what we call a full limit to exist at a particular point, the right-hand limit must equal to the left-hand limit. Okay, so in other words, the limit as x approaches a of f of x equals L is only true if and only if the limit from the right is equal to the limit from the left. So anytime you've got a function that has a jump discontinuity, and you're looking at the limit as you're approaching the value where the jump occurs, you have to look at the left-hand limit and the right-hand limit. When there's a jump, then the full limit would not exist. So let's look at some graphical representations of limits. So on this graph, we've got a vertical asymptote. Okay, so we know what happens on vertical asymptotes. The graph never crosses it. We've got a hole here. We've got another hole here. We've got these points that fill up those that are located at the same x values of those holes. So when we are talking about the limits graphically, what we're looking at again is what is the y value as x approaches a particular value. So for A, as x is approaching 4, what's the y value approaching? So find my 4, 1, 2, 3, 4. And so here is where x is equal to 4. So as the function is approaching 4 from the left, follow the function from the left and from the right are both approaching where that hole is. Notice that the function is actually defined up here where this point is, but that's not where the y value is approaching. The y value is not approaching that point. The y value is approaching where this hole is. And so the limit of that function then is going to be the y value that it's approaching, which is where the hole is. So it's going to be equal to 2. Okay. On B, the limit as x approaches 0. Well, here's where 0 is located. From the left and from the right, the y value that I'm approaching is equal to 1. Erase some of this writing here. C, the limit as x approaches 2 from the left. Okay, so I'm only concerned about coming from the left as I'm approaching 2. So approaching 2 from the left, notice that it's going downwards. And it's not where it's equal, but it's where it's approaching, so it's heading down to negative infinity. So the limit is at negative infinity. Coming from the right, as x approaches 2 from the right, the y value that I'm approaching is up here at 1, 2, 3, 4. Notice it's not what it's equal to, it's what it's approaching. So it's approaching 4. Can you give me 5 minutes?
Yeah.
I'm finishing a recording. So the limit as x approaches 2 from the right is equal to 4. On E, the limit as x approaches 2, because there's not a right or a left, we're talking about the full limit. And so in that case, the limit from the left would have to be equal to the limit from the right in order for the full limit to exist. And because the limit as I'm approaching 2 from the left is not the same as the limit as I'm approaching from the right, then this limit does not exist. And we use the letters D and E to represent does not exist. Okay, D and E is what we write as a shorthand for does not exist. Okay, look at the next one. F says the limit as x approaches negative 1 from the left. So here's negative 1. From the left, I'm heading up towards positive infinity. So that limit would be positive infinity. G says the limit as I'm approaching negative 1 from the right. So from the right, I'm heading up towards positive infinity again. So the limit as x approaches -1 from the right is also positive infinity. So when I'm talking about the full limit then here in h as x approaches -1, because the limit from the left is the same as the limit from the right, then the full limit is equal to that same value. And so remember that limits are y values that your function is approaching, but not necessarily what it is equal to. Okay, you're looking for what it's approaching, the y value it's approaching as x approaches a specific value.